Hi, and welcome to the first training video of the Living Landscapes project. In this video, we'll give you a basic understanding of what Lidar is and how it works. So Lidar, which stands for Light Detection and Ranging, is what we call an active remote sensing technique. This means it sends out its own energy in the form of light to measure the shape and elevation of the Earth's surface. Specifically, Lidar uses near-infrared light to measure the ground. Unlike passive remote sensing techniques, such as your camera or satellite, that relies on the sun's energy to measure surfaces, Lidar operates independently of external light sources. Lidar is also a non-intrusive technique, meaning it does not physically touch or disturb the landscape it measures. This makes it ideal for surveying sensitive areas such as archaeological sites without causing damage. Lidar cannot scan underground. It measures only the topography and elevation of the Earth's surface, not what lies beneath it. So Lidar works by sending out rapid bursts of laser light known as pulses from a sensor mounted on a drone, plane, or a vehicle. These pulses travel through the air until they hit an object, such as the ground, a tree, or a building, and then they bounce back to the sensor. This reflected light is called a return. So in this example, the red hashed line represents the LiDAR pulse being sent from the sensor. As it travels downward, the first surface it touches is the top of a tree branch. This reflection reaches the sensor the fastest and is called the first return. The pulse may then continue through the gaps in the canopy, bouncing off lower branches and producing second or third returns. If the pulse makes its way all the way to the bare ground, that final reflection is known as the last pulse return. It takes the longest to reach the sensor and is used to calculate ground elevation. Lidar can't pass through solid objects, so if the pulse hits something like a building, it won't reach the ground beneath. In that case, the last pulse return will become the roof, not the earth below. So by measuring how long it takes for each pulse of laser light to return to the sensor, Lidar calculates the distance to the object it has hit. This is done using the time of flight principle, where the system multiplies the time taken by the pulse to travel to the object and back by the speed of light, then divides it by 2, since the pulse travels to the object and back. The formula is time times the speed of light divided by 2, which gives us the distance. Once the distance is known, Lidar uses the altitude of the sensor to calculate elevation. This is done by subtracting the measured distance from the sensor's altitude. So our equation is altitude minus the distance gives us elevation. So this gives us the height of the object or ground surface below the sensor. Some pulses only reflect once, such as when scanning a flat surface. But in more complex environments like forests, a single pulse can bounce off multiple surfaces, starting with the treetops, then lower branches, and finally the ground. Each of these reflections is recorded as a separate return, and the time difference between them allows the system to calculate the height and structure of everything the pulse interacts with. This ability to capture multiple returns from a single pulse helps build a highly detailed 3D model of the landscape, showing both the terrain and the vertical features above it, such as vegetation or built structures. So after a LiDAR flight, the data collected is processed into what's called a point cloud. This is a dense collection of millions and billions of individual points in 3D space. Each point represents a return from a laser pulse that bounced off a surface and came back to the sensor. These points are recorded with three values: our X value, which is our easting, our Y value, which is our northing, and our Z value, which is elevation. Together, they form a detailed digital model of the landscape. But the point cloud is just a collection of dots. It doesn't yet look like a smooth surface or a usable map. That's where interpolation comes in. So interpolation is the process of filling in the gaps between those dots to create a continuous surface. It's like connecting the dots to form a picture. Since LiDAR pulses don't hit every single spot on the ground, we use nearby points to estimate what the elevation should be in between. This allows us to generate models like digital terrain models or digital surface models, which show the shape of the land or the tops of objects like trees and buildings. In short, interpolation transforms raw LiDAR pulses into readable, usable surfaces. It's the step that turns scattered returns into something we can actually see, measure, and analyse, whether we're mapping archaeological features, planning land use, or studying environmental change. Interpolated LiDAR images give us a general sense of the landscape shape, but they often don't reveal the finer details we're looking for, especially when it comes to subtle archaeological features. To enhance the visibility of the topography, we need to manipulate the data by adjusting how light interacts with the surface. This helps bring out small changes in elevation that might otherwise go unnoticed. Techniques like hill shading, slope analysis, and simple local relief modelling can dramatically improve what we see. And we'll explore these methods in more detail in the next video, where we focus on LiDAR visualizations and how to interpret them. So far, I've shown examples of what the end product of interpolation looks like, which are smooth surfaces created from LiDAR point clouds, as well as visualizations where the data has been further manipulated to enhance detail. These images help illustrate how LiDAR can reveal the shape of the landscape and highlight subtle features. However, there's a key step that happens before we get to those results. During the interpolation process, we need to decide what kind of image we want to create. That decision determines whether we produce a digital surface model, a DSM, or a digital terrain model, a DTM. So a digital surface model, the DSM, includes all the returns from each LiDAR pulse. It means it captures everything the laser hits: trees, buildings, vehicles, and any other surface features. It gives us a view of the landscape as it appears above ground. A digital terrain model, so a DTM, on the other hand, uses only the last pulse return. This is typically the bare ground, after the pulse has passed through gaps in vegetation or bounced off lower surfaces. To create a DTM, we filter the point cloud by instructing the software to remove all returns except the last one. Then we interpolate using just those ground points to build a clean model of the terrain, free from surface clutter. This filtering step is crucial. It's what allows us to focus on the true shape of the land, which is especially important for archaeological analysis, as it allows us to detect human-made features that might be obscured and hidden in vegetation. So here's an example from Welshbury Hill in Gloucestershire. What we're looking at is a vertical bird's eye aerial photograph of the area. From this image, we can clearly see a dense woodland canopy covering the landscape. Now, we're looking at a manipulated image derived from LiDAR data. This is a DSM, so a digital surface model. And as you can see, the tree canopy is still clearly visible. Even though we've processed the data, the surface features remain intact because this model includes all the returns. It gives us a realistic view of the landscape, but it doesn't reveal what's beneath the vegetation. Our next image is a digital terrain model, so a DTM, of the same location. This model only shows the last pulse returns, meaning the trees and other surface features have been removed from the data. Now we can clearly see the archaeological features that were hidden beneath the woodland canopy. What we're looking at are banks and ditches, also known as ramparts, which were constructed during the Iron Age, somewhere around 2,700 years old. These ramparts formed part of a hill fort, a defensive enclosure built on elevated ground. Surrounding the hill fort are a series of rectangular patterns. These are field systems, which are older than the hill fort itself. Field systems are the physical remains of ancient farming practices. During the Living Landscapes project, we'll be working with data derived from a digital terrain model. This approach allows us to interpret the landscape in its rawest form and uncover traces of past human activity that are invisible in standard aerial imagery or digital surface models. So just a bit of a recap. So we've covered the fundamentals of LiDAR, how it captures data, and the steps we take to turn that data into meaningful surfaces. You've seen how we go from raw point clouds to interpolated models, and how choosing between a digital surface model and a digital terrain model shapes what we can see. We've also looked at how manipulating the data helps us reveal subtle archaeological features that would otherwise stay hidden. Thanks for watching, and I'll see you in the next session.